Hi all, I'm here to take a seminar on communication for space exploration. These are the contents are included in this seminar, which includes introduction, history of space exploration, how space communications work, types of space communication system, space communication bands, applications, emerging trends in the field of space, challenges, companies involved, and finally, conclusion. Introduction. Now, space communication is also known as satellite communication, is a foundational element of modern space exploration. It plays a vital role in exchanging information between entities in space and between space and Earth, profoundly impacting various industries and our daily lives. One driving force behind space communications enhancement is the ever increasing need for high speed data transmission. In our interconnected world, the capability to transmit vast volumes of data quickly and reliably is paramount. The rapid evolution of space communication technologies has enabled the contest of long distance communication challenges, empowering global connectivity and unlocking new possibilities across scientific research, satellite operations, telecommunication, broadband, improving healthcare, and navigation system. Furthermore, space communication finds applications across numerous domains. It has revolutionized healthcare through telemedicine and remote diagnostics. It plays a vital role in disaster management and emergency response and fostered international collaboration in space exploration missions, enhancing our collective understanding of the universe. Next is the history of space exploration. In 1609, Galileo Galilei recorded the first telescopic observation of the night sky using a telescope. Later, in 1781, William Herschel discovered the first telescopic planet, which is Uranus. In 1957, Sputnik 1, which is the first artificial satellite, carried a simple radio transmitter into space. In 1960, Apollo program, which was launched by the US, it was in order to land humans on the moon and return them back to Earth. Next, in 1962, the Tesla 1 was launched also by the US. It is the first active communication satellite. It enabled the transmission of telephone signals, calls, and data globally. In 1977, Voyager 1 and 2 was launched. It was in order to send back data from outer solar system. Later in 1981, the Space Shuttle program, which was the first partially reusable spacecraft of the US. In 1990, the Hubble Space Telescope was discovered. It was the first large optical telescope. In 2013, Mangalyaan, which was India's first interplanetary mission reaching to the Mars orbit, was launched. In 2020, the Perseverance rover, it was launched to the Mars. It was in order to find any past or microbial life for the future study. In 2022, the James Webb Space Telescope was discovered. It was in order to observe the universe in the infrared light. Now, currently in 2023, India's ISRO successfully lands Chandrayaan 3 on the moon's south pole. And Aditya L1, it is a mission to study the sun's corona from the L1 Lagrange point. Moving on, how space communication works. Now, space communications use a combination of orbiting satellites above the Earth and ground stations to transmit and receive information from one point on Earth to another. Now, there are three stages involved in the working of space communications, which includes uplink, transponders, and downlink. The first stage of space communication is the uplink. Now, in this stage, data or signals are transmitted from a ground station on Earth to a satellite in space. The ground station typically uses large antennas to send the signals, which are then transmitted as radio waves or laser beams. These signals carry various types of information, such as commands for the satellite, scientific data, or even television broadcast. Now, once the signal reaches the satellite, they are received by the satellite's antenna. The satellite's onboard equipment processes and amplifies the signals, preparing them for the next stage of communication. Now, this stage is critical for ensuring that the signals are strong enough to be transmitted back to the Earth. Now, the next stage is the transponders. Now, transponders are electronic devices on board the satellite that receive the signals from the ground station and retransmit them back to Earth. They act as communication relays, amplifying and modulating the signals to improve their quality and strength. Transponders are designed to operate within specific frequency bands such as S band, C band, X band, etc., depending on the requirements of the mission or application. Now, the final stage is the downlink. Now, in this stage, the satellite transmits the processed signals back to Earth. The signals are received by ground stations equipped with large antennas that capture the signals and convert them into usable data. The ground station then processes the received signals, which can include decoding the data, extracting images or scientific measurements, or relaying the information to the intended recipients. Next is the type of space communication system. Now, space communication encompasses various types of systems that facilitate the exchange of information between entities in space and Earth. Now, here the two primary types of space communication system are laser communication and radio frequency communication. Laser communication. Laser communication is also known as optical communication. It utilizes laser beams to transmit data between spacecraft and ground stations. Now, this technology offers several advantages, including high data rates, secure communication, and immunity to electromagnetic interference. Laser beams can carry large amounts of information due to their narrow beam divergence, enabling higher bandwidths compared to traditional radio communication. This makes laser communication particularly useful for transmitting large data sets such as high resolution images or scientific measurements from spacecraft to Earth. Additionally, laser communication systems can provide secure communication channels as laser beams can be precisely directed and are less susceptible to interception compared to radio waves. However, laser communication requires a direct line of sight, between the transmitting and receiving points, which can be challenging to maintain in certain circumstances. Now, the infrared light packs the data into significantly tighter waves than radio waves. This means that the information signal is encoded onto the laser beam by varying the amplitude of the light wave. Now, it also works on the principle of amplitude modulation process. Now, it typically involves a transmitter. Now, this is a device that generates a narrow and intense beam of coherent light that uses a laser diode. Now, here it uses a quantum dot laser diode. It offers high performance in terms of wavelength, line width, and efficiency. Now, the light emitted is typically in the infrared or visible spectrum. Next is a modulator. Now, it encodes the data onto the laser beam using various modulation techniques like amplitude modulation, frequency modulation, or phase modulation. Next is a receiver. It includes a photodetector which captures the incoming laser beam, and the data encoded in the beam is decoded. And the final stage is the demodulator. Now, the received signal is demodulated to recover the original data. Now, this process reverses the modulation applied at the transmitter end. Now, the next type of communication is the radio frequency communication. Now, it is the most widely used and established method of space communication. It relies on radio waves and antennas to transmit and receive signals between the spacecraft and ground stations. Now, radio waves have longer wavelengths compared to laser beams, allowing them to propagate through the Earth's atmosphere and other obstacles. Now, this makes radio communication suitable for long distance communication and enables communication with spacecraft located in orbit or even in deep space. Now, the bands are carefully allocated to avoid interference and ensure efficient communication. Now, radio communication provides reliable links for various purposes, including telemetry, command and control of spacecraft, voice and data transmission, and even deep space missions like the interplanetary exploration. Now, its frequency range from 3 kHz to 300 GHz. Now, the process involves 4 steps, which includes generation. Now, they generate an electromagnetic wave using a transmitter. The transmitter converts an electrical signal into an electromagnetic wave by oscillating electrons in an antenna. Next is the modulation. They modulate the carrier wave with the information signal. Next is the transmission. Once the carrier wave is modulated, it is amplified and transmitted through the air using an antenna. The final process is the reception. At the receiver, the antenna converts the electromagnetic wave back into an electrical signal. Now, the electrical signal is then demodulated to recover the original information signal. Now, the choice between laser communication and radio communication depends on specific mission requirements. While laser communication offers higher data rates and secure communication, it is limited by line of sight constraints. On the other hand, radio communication provides reliable long distance communication but with lower data rates compared to laser communication. Now, both types of system have their own advantages and limitations, and their success depends on factors such as mission objective, distance, bandwidth requirements, and available resources. Next is the space communication band. Now, space communication bands are the frequency bands that are used to communicate with space craft and their objects in space. It relies on specific frequency bands to establish robust and reliable connections for the celestial objects. Now, these frequency bands serve as the backbone of interplanetary communication, allowing for the transmission of critical data and commands. So, the commonly used space bands are L band. It ranges from 1 to 2 gigahertz. They are used for mobile and satellite to satellite communication. It is suitable for global navigation, satellite system, mobile satellite services, and some satellite communication links. Next is the S band. It ranges from 2 to 4 gigahertz. Now, S band is the powerhouse of space communication, operating within the frequency range of just as I said, 2 to 4 gigahertz. It provides a balance between signal penetration through Earth's atmosphere and the ability to carry a significant amount of data. Now, S band is widely used for telemetry, tracking, and control of spacecraft, making it instrumental in missions like lunar exploration and deep space probes. Next is the C band. It extends from 4 to 8 gigahertz and offers a compromise between signal strength and potential interference. It finds extensive use in weather radar systems and satellite communication. While less commonly used for space exploration, C band remains an important option for specific missions. Next is the X band. It operates in the 8 to 12 gigahertz range and provides higher data transfer rates compared to lower frequency bands. Its advantage lies in its resistance to radio interference and rain attenuation, making it ideal for high data rate applications. X band is often utilized in deep space missions, including those exploring the outer planets. Next is the Q band. It ranges from 12 to 18 gigahertz and is well suited for broadband satellite communication. It offers a balance between data transfer rates and the ability to maintain signal strength along long distances. Now, Q band is commonly used in geostationary satellites for services such as television broadcasting and internet connectivity. Next, we have the K band. K band is a higher frequency band used for satellite communication, radar, and terrestrial microwave links. Now, K band is often chosen for satellite uplinks and downlinks due to its higher data rate capabilities. Next is the Ka band. It ranges from 18 to 27 gigahertz. It is used for high capacity data communication and is common in satellite broadband services and some deep space missions. It offers even higher data rates and requires more precise pointing due to its higher frequency. Next is the applications. The first one is telecommunication. Now, space communication has revolutionized global telecommunications, enabling long distance voice and data transmission. Now, satellites act as communication relays, facilitating telephone calls, video conferencing, internet connectivity, and broadcasting services. They provide coverage to remote areas, connect regions with limited terrestrial infrastructure, and support disaster response by establishing communication networks in affected areas. Next, we have aviation communication. Now, satellite communication is crucial for air traffic control and aviation safety. Now, airplanes use satellite communication system for navigation, weather updates, and communication with air traffic control centers. Next, we have the Earth observation. Now, space communication allows for the collection and transmission of vast amounts of data from Earth observation satellites. These satellites capture images, monitor environmental changes, track weather patterns, and provide valuable data for climate research, disaster management, agriculture, urban planning, and natural resource management. Space communication ensures the efficient transfer of this data to ground stations and research institutions for analysis and decision making. Next, we have broadcasting and media. Now, satellite television and radio broadcasting rely on space communication to distribute content across vast areas, providing access to information and entertainment for millions of people. And finally, we have navigation. Now, the Global Positioning System, which is the GPS, and other satellite communication navigation systems use space communication to provide precise location and timing information to users worldwide. Next, we have the challenges in space communications. Now, the first one is the distance and delay. Now, the vast distances between spacecraft and Earth or between spacecraft themselves introduce significant time delays in communication. Now, signals can take several minutes or even hours to travel between locations, making real-time interactions difficult or impossible. Now, the solution for this is developing and utilizing high frequency bands such as optical communication, which can transmit data as much higher speed and can reduce the latency. Now, next is the atmospheric interference. Now, the Earth's atmosphere can interfere with radio frequency signals, causing signal attenuation, fading, and stellionation. Now, this can affect the quality and reliability of communication links, especially during periods of high activity in the ionosphere. Now, the solution for this is adapting coding and modulation techniques to adjust signal transmission parameters based on real-time atmospheric conditions, mitigating the effects of interference. Now, next is the cost consideration. Now, developing and deploying space communication system can be expensive, requiring significant investments in infrastructure, launch cost, and ongoing maintenance. Now, this can limit the scope and capabilities of space communication. Now, the solution for this challenge is opting for reusable rockets, which we will be discussing in the next slide. Now, next is the security concerns. Now, space communication links are vulnerable to eavesdropping and interference, making it crucial to implement robust security measures. Now, this includes encryption, authentication, and anti-jamming techniques. Now, the solution for this is implementing advanced encryption algorithms and key management protocols to protect sensitive data transmitted over space communication challenges. Now, next is the emerging trends in the field of space. First is the reusable rockets. Now, in recent years, companies like SpaceX and Blue Origin have revolutionized space exploration by pioneering the development of reusable rocket technology. Now, reusable rockets are launch vehicles that are designed to be recovered and relaunched multiple times. Now, the traditional rockets provides noise, visual and thermal radiation, chemical emission, and debris pollution. Now, in order to avoid this situation, companies like SpaceX and Blue Origin have developed reusable rockets like Falcon 9 and Falcon Heavy and Blue Origin's New Shepard. Now, they significantly reduce launch cost and environmental impact by eliminating the need to build a new rocket for new launch. Now, they dramatically reduce launch costs, just like I said, by recovering and refurnishing the rocket companies. These companies have made space more accessible and economically viable. These are the examples of the reusable rocket. The first one, the figure 3 shows SpaceX Falcon 9 and figure 4 shows Blue Origin's New Shepard. Next is space tourism. Now, another exciting trend in space exploration is the burgeoning field of space tourism. Now, space tourism is the commercial activity of sending private individuals into space. It involves providing paying customers with the opportunity to experience space travel, weightlessness, and the unique views of Earth from space. Companies are making strides in offering suborbital and orbital flights for the civilians, and the space tourism is becoming increasingly accessible to civilians who aspire to experience the wonders of space. Now, companies like SpaceX with Crew Dragon and Blue Origin's New Shepard is also a prominent example. Now, the figure shows Virgin's Galactic Spaceship 2 and figure 6 shows SpaceX Crew Dragon. And finally, the companies involved in space exploration. First one is the Dhruva Space. It is based in India. Now, they develop satellites that are flexible and scalable, making them ideal for a variety of space communication applications. Next is the Rocket Lab. It is a New Zealand based company. Now, Rocket Lab is developing the Photon Space Bus, which can be used to carry small satellites into orbit. Next, we have the Lockheed Martin. It is a US based company. Now, they are a major designer and manufacturer of satellites for communication, navigation, and remote sensing applications. Next is the Northrop Grumman, which is also a US based company. Now, it provides satellite navigation and communication for NASA missions, including Lunar Gateway and Dragon spacecraft. Next, we have SpaceX, which is a US based company. Now, SpaceX is developing the Starlink satellite constellation, which will provide global broadband internet access. Now, next is the Honeywell Aerospace. It is also a US based company. Now, they provide communication and navigation systems for aircraft like ISS, Space Shuttle, and Orion. Next, we have Boeing Co. Now, it designs, manufactures, and launches satellites for communication, navigation, and remote sensing. Now, Boeing also provides ground stations and other infrastructure for space. And last is the Skyroot Aerospace. It is also Indian based company. Now, Skyroot Aerospace is a private space technology company that is developing launch vehicles to launch satellites and other payloads into orbit. So now we have come to the conclusion. Now, space communication is a vital part of space exploration. Now, space communication play a vital role in space exploration. satellite operations, satellite research, and also in our day to day life. Now, the history of space exploration is displayed to demonstrate the flow of innovations in the space fleet. An overview of the types of space communication system was also examined. Now, various space communication bands are being explored. The challenges that space communication face are studied. Some emerging technologies like reusable rockets and space tourism that had occurred in the last few years have also discussed. Now, the companies involved in space communications are also explored. These are the references I used for the seminar. Thank you.